Hello, I'm Sergey, and I'm going to introduce you our recent work on revisiting profile inference in compilers. This is a joint project with my colleagues, Wenlei, Julin, Lei, and Hongtao. The area we're working on is called profile-guided optimization. PGO is an important part in most modern compilers that is used for improving the performance of large data center applications. The basic idea is visualized on the diagram. The classical compilation process is split into two steps. A binary built on the first traditional step is executed on relevant benchmarks and profile data is collected. The profile describes dynamic behavior of the binary, such as the execution frequencies of basic blocks and function invocations. Then the information is used on the second step of the compilation and guides the compiler to apply optimization passes more selectively and effectively. In practice, PGO often provides double-digit performance boost, and therefore it is essential for large-scale applications. We've noticed, however, that the impact of PGO heavily depends on the quality of profile data. While instrumentation-based PGO operates with high-quality profiles, in most practical applications, it introduces enormous runtime and operational overhead. As a result, a lightweight sampling-based PGO is the state-of-the-art technology. A disadvantage of sampling-based PGO is that it's not delivering the same level of performance boost compared to the instrumentation-based counterpart. The reason is a worsened quality of utilized profile data. Therefore, an important problem in the area is so-called profile inference or profile correlation, where the goal is to improve and correct inaccuracies in collected profile datasets. Let me now summarize our main contributions. First, we identify and formalize the underlying problem of profile inference. It turns out that the quality of profile data suffers, for example, from sampling noise and hardware bias. Another source of inaccuracies is the fact that we collect so-called binary level profile, while a compiler needs a source level profile data. And the mapping between these two is often not obvious, and sometimes it's even impossible to correctly attribute collected samples to the corresponding intermediate representation of the code. In this paper, we managed to formally describe the optimization problem of reconstructing the most realistic profile from an incomplete dataset. Our model is based on objectives and constraints capturing the desired properties of ground truth profile data. Our second contribution has an algorithmic flavor. We study theoretical aspects of the new graph problem, and we show that it is computationally APX hard. That is, it's unlikely that an efficient algorithm solving the problem optimally exists. With this in mind, we designed and implemented a theoretically sound heuristic. Our approach is based on solving a variant of the classical minimum cost maximum flow problem, in which we basically had to replace and re-engineer all components of the classical algorithm. The resulting implementation runs in subquadratic time, which makes it an attractive approach for processing large binaries. And last but not least, we implemented our technique in LLVM, and it's currently used to power sampling-based PGO of the compiler. Our extensive evaluation on synthetic benchmarks and a few production workloads shows that the new profile inference algorithm that we call Profi already provides measurable performance benefits. What is probably equally important is that the work opens the door for other compiler optimizations that were not beneficial or practical due to the poor quality of profile data. To conclude, we invite everyone to read the paper or to watch the full version of the presentation. We will discuss practical issues of PGO in more details. And I promise everyone to show some very cute theoretical questions, as well as highlight interesting open directions in the area. Thank you.